welcomes to the St. Joseph College for Women Autonomous Vishakhapatnam. Department of Mathematics welcomes you for the online course on real analysis. And the module 3 is Differentiation and Mean Value Theorem. I introduce myself as Venkat Lakshmi, Assistant Professor, Department of Mathematics, St. Joseph College for Women Autonomous Vishakhapatnam. Now we are going to discuss the most important theorem in the differentiation, that is the Rolle's theorem. What is the statement of Rolle's theorem? If a function f is mapping from closed interval ab tends to R is such that first one f is continuous and closed interval ab, second one f is derivable and open interval ab, and third one f of a is equals to f of b. Then there exists an element C belongs to open interval AB such that f dash C is equal to 0. This is the statement of Rolle's theorem. Now proof. Given that f is mapping from closed interval AB tends to R is such that what are the three conditions of Rolle's theorem? F is continuous at closed interval AB, f is derivable and open interval AB, and f of A is equals to f of B. Now we prove that there exists an element C belongs to open interval AB such that f dash C is equals to 0. For that, f is continuous in closed interval AB implies f is bounded on closed interval AB and attain its bounds also. What is the definition of f is bounded? There exist two elements C, D belongs to closed interval AB such that f of C is equals to capital M. Capital M means what? Supremum of f. And also f of D is equals to small m. Small m in the sense infimum of f. There are two possibilities. Either supremum is equals to infimum. That is m is equals to capital M is equals to small m, or supremum not is equals to infimum, which means capital M not is equals to small m. Now here we have two cases, that is case 1 and case 2. What is case 1? If supremum is equals to infimum, which means capital M is equals to small m. For that, f of x is equals to, we are taking infimum, that is small m, for all x belongs to closed interval a comma b. F is constant function on closed interval ab implies f dash x is equals to 0 for all x belongs to closed interval AB. Therefore, f dash C is equals to 0 where C belongs to open interval AB. That is case 1. What is case 2? If capital M not is equals to small m, which means supremum not is equals to infimum. Therefore, f of A is equals to f of B and supremum not is equals to infimum. Capital M not is equals to small m. We have either f of A not is equals to capital M in the sense supremum and capital B not is equals to capital M, which means supremum, or f of A not is equals to small m and f of B not is equals to small m. Small m in the sense infimum. Therefore, capital M is equals to f of C not is equals to f of A. That implies C not is equals to A. Same, capital M is equals to f of C not is equals to f of B. There implies C not is equals to B. Therefore, A less than C less than B. Then whenever we have A less than C less than B, C belongs to, C exists in open interval a comma b. So f is derivable on closed open interval AB. That is, C belongs to open interval a comma b. So then implies f is derivable at C, which means f dash C is equals to left hand limit f dash C is equals to right hand limit f dash C. Now supremum of f is equals to capital M, that is equals to f of C. So that implies f of C minus h less than or equals to f of C and f of C plus h less than or equals to f of C. Now we have to prove that L f dash C is equals to R f dash C. For that, f of C minus h greater than or equals to 0. That implies f of c minus h minus f of c less than or equals to 0. Whenever we have multiply with minus above inequality, then greater than become a less than. So that f of c minus h minus f of c by minus h greater than or equals to 0, which means we are dividing by minus h on both sides, then 0 by anything, the value become a 0. Apply limits on both sides, then we get limit h tends to 0 f of c minus f of c minus h by h greater than or equals to 0, which is nothing but definition of left differentiable L f dash c greater than or equals to 0. Similarly, f of c plus h less than or equals to f of c, which means f of c plus h minus f of c less than or equals to 0. f of c plus h minus f of c by h less than or equals to 0. Apply limits on both sides, then we get limit h tends to 0 f of c plus h minus f of c by h less than or equals to 0, which is the definition of right differentiable, that is r f dash c less than or equals to 0. From this and this, f dash c is equals to, f dash c is nothing but L f dash c, that is equals to r f dash c. L f dash c greater than or equals to 0, r f dash c less than or equals to 0. That implies f dash c is equals to 0. Now we discuss about problems on Rolle's theorem, the most important problems on Rolle's theorem. Verify Rolle's theorem in the interval, closed interval a b for the function f of x is equals to x minus a whole to the power of m, x minus b whole to the power of n, where m comma n are positive integers. Then solution. How to verify Rolle's theorem on the given problem? The given function f of x is equals to x minus a whole to the power of m, x minus b whole to the power of n, where m comma n are positive integers. This is a polynomial function of m plus nth degree. The given function is a m plus nth degree polynomial. So first one trivially satisfied, means f is always constant on closed interval ab, because constant function always continues. And second one, f is a derivable on closed interval ab. Then the third condition, f of a is equals to f of b, it is trivially satisfied. Always f of a is equals to f of b is equals to 0. So f satisfies all these three conditions on Rolle's theorem. Then we have to prove that one element in open interval ab, which means there exists c belongs to open interval ab such that f dash, what is the function f of x is equals to x minus a whole to the power of m, x minus b whole to the power of n. This is the given function. Now we have to prove that c belongs to open interval ab. For that, f dash x is equals to, what is the derivative of f of x? F dash x is equals to m into x minus a whole to the power of m minus 1, n into x minus b whole to the power of n, plus, in this case, x minus b whole to the power of n treated as a constant. Plus next, plus x minus a whole to the power of n, in this case, x minus a whole to the power of m as a constant, n into x minus b whole to the power of n minus 1. F dash c, substitute in place of x c, the element c, then we get f dash c is equals to m into c minus a whole to the power of m minus 1, c minus b whole to the power of n, plus, in place of x we are substituting c minus a whole to the power of m, n into c minus b whole to the power of n minus 1, that is equals to 0. c minus a whole to the power of m minus 1, c minus b whole to the power of n minus 1, take outside common, because these two terms having a common term, that is c minus a whole to the power of m minus 1, c minus b whole to the power of n minus 1. Then what is the remaining term? M into c minus b plus n into c minus a, that is equals to 0. Then this implies m into c minus b plus n into c minus a is equals to 0, because c minus a whole to the power of m minus 1, c minus b whole to the power of n minus 1 taking to RHS side, then it becomes a 0. Now multiply with m into x c minus b plus n into c minus a is equals to 0. Then we get mc minus mb plus nc minus na is equals to 0. From both terms, m plus n take outside, m plus n into c, that is equals to remaining terms minus mb taking to rh side. Minus become a plus. Then we get mb plus mb plus na. So we want c, the constant c value. For that, taking m plus n taking to rh side, send to rh side. Then we get c is equals to mb plus na by m plus n, which belongs to always open interval ab, because c lies in open interval ab, because here m comma n are positive integers, so that clearly it lies in open interval ab. Then Rolle's theorem is verified. And Rolle's theorem is now next problem on Rolle's theorem. Examine the applicability of Rolle's theorem for f of x is equals to 1 minus x minus 1 whole to the power of 2 by 3 on closed interval 0, 2. Solution. The given function f of x is equals to 1 minus x minus 1 whole to the power of 2 by 3 on 0, 2. Now derivative of f of x. F dash x is equals to minus 2 by 3 x minus 1 whole to the power of 2 by 3 minus 1. So, like a derivative of x to the power of n, d by dx of x to the power of n is equal to n into x to the power of n minus 1. Clearly it is in the form of x to the power of n. So that minus 2 by 3 x minus 1 whole to the power of minus 1 by 3. That is equals to 2 minus 2 by 3, 3 into x minus 1 whole to the power of 1 by 3. Clearly, f is not a derivable at x is equals to 1. The second condition of Rolle's theorem is not satisfied. What are the three conditions of Rolle's theorem? F is a continuous on the closed interval a b, f is a differentiable at x closed interval a comma b. Then third one, f of a is equals to f of b. So clearly, Rolle's theorem is not applicable for the given function f of x is equals to 1 minus x minus 1 whole to the power of 2 by 3 on closed interval 0, 2. The next problem on Rolle's theorem. What is the given problem? Show that there is no real number k for which the equation x cube minus 3x plus k is equals to 0 has two distinct roots in open interval 0, 1. Solution. The given function x cube minus 3x plus k is equals to 0. Suppose, if possible, f of x is equals to 0 has two distinct roots alpha comma beta in open interval 0, 1. Let 0 less than alpha less than beta less than 1. Clearly, alpha comma beta lies in 0, 1. F of x is a polynomial of third degree. The given function f of x is a polynomial of third degree. F is a continuous on closed interval a comma b. F is a derivable on open interval a comma b. And f of alpha is equals to f of beta, that is equals to 0. By Rolle's theorem, there exists an element c belongs to open interval a comma b such that f dash c is equals to 0. Which means we are substituting in place of x, the value is a c. Then we get 3c cube minus 3c, that is equals to 0. So 3c square minus 3 is equals to 0. Take out 3, will get c square minus 1 is equals to 0. 3 transfer to rh side, 0 by 3 the value is 0. Then we get c square minus 1 is equals to 0. Then c square is equals to 1, c is equals to plus or minus 1, which is a contradiction. Therefore, there is no real number k for which the equation x cube minus 3x plus k is equals to 0 has two distinct roots in open interval 0, 1. Next, we are going to discuss the most important theorem in differentiation. The theorem name is Lagrange's mean value theorem. What is the statement of Lagrange's mean value theorem? If f is mapping from closed interval a comma b tends to R is a function such that
we have two conditions here. F is a continuous and closed interval a comma b. F is derivable on open interval a comma b. Then there exists C belongs to open interval a comma b such that f dash c is equals to f of b minus f of a by b minus a, which means f dash c. Proof. The given function f is mapping from closed interval a comma b tends to R is a function such that first one, f is continuous and closed interval a comma b, f is derivable and open interval a comma b. Now we have to prove that there exists an element c belongs to open interval a comma b such that f dash c is equal to f of b minus f of a by b minus a. For that we are defining one function, that is phi of x is equals to f of x plus ax for all x belongs to closed interval a comma b and a belongs to R. A is a constant function to be determined such that phi of a is equals to phi of b. Therefore, f of a plus capital A into a is equals to f of b plus a into small b, which means capital A minus capital A b is equals to f of b minus f of a. That implies a into a minus b is equals to f of b minus f of a, which means f is a continuous on closed interval a comma b, always constant function is closed interval a comma b, then f of x plus ax is also continuous on closed interval a comma b. Continuation of Lagrange's mean value theorem. Now we are finding a value, that is a is equals to f of b minus f of a by a minus b. This is the equation 1. Let it mean equation 1. Therefore, f is continuous and closed interval a comma b, comma the constant function ax is a derivable on R. That implies phi of x is also continuous and closed interval a comma b. Therefore, f is derivable on open interval a comma b. Always constant function is derivable. Then ax is a derivable on R. That implies phi of x is derivable on open interval a comma b. Therefore, phi of x satisfies all the conditions on Rolle's theorem. Then there exists c belongs to open interval a comma b such that phi dash c is equals to 0. F dash c plus a is equals to 0. F dash c is equals to minus a. We know that minus a value, that is minus f of b minus f of a by a minus b. F of b minus f of a by b minus a. Therefore, f dash c is equal to f of b minus f of a by b minus a. This is the Lagrange's mean value theorem. Thank you.